So as I mentioned that the best solution against the DNS poisoning attacks is to implement DNSSEC or DNS security. DNSSEC is basically a security extension to the DNS protocol, which is going to prevent against the DNS attacks by digitally signing all the responses using public key cryptography. Now, once you use the public key cryptography and you sign them with uh, the the DNS response with the private key, then it becomes really difficult for the attackers to launch poisoning attacks because the information um, will be authenticated based on the public key of the signer, and then since the attacker doesn't have the private key, his DNS response will not be verified. Now, the problem with the DNSSEC is that the deployment of DNSSEC is quite complicated, and even the major companies, bigger companies, they have not implemented DNSSEC because of the complexity. We'll talk a bit more about the complexity shortly. So one of the major challenges is that who is going to manage the root name servers and their private keys, which is one of the major issues in implementing the DNSSEC. So until or unless the DNS security is implemented, the DNS poisoning attacks and other attacks related to DNS protocol will still exist. Now, what DNSSEC guarantees is that the information or the responses that a client is receiving, they are authenticated, that the actual authoritative name server has sent the reply. It will also guarantee that the information is not modified, the response is not modified. And also it will verify the authenticity of those domains which do not exist, that we saw that in the previous discussion, that the attackers, they usually send non-existent domains request and then reply by themselves. So the authenticity of that information will also be guaranteed. Now, this can only be accomplished by signing the DNS replies by using the private key, as I mentioned. So let's have a look at how this DNSSEC actually works. Now, once you implement DNSSEC, it will contain some additional information along with the DNS records. Three new informations that are included is RSIG, which is resource record signature, the DNS key, and the designated signer. So, for example, if a client issues a DNS request, it indicates that it supports the DNS SEC. If the queried authoritative name server, let's say for the authoritative name server of Google, if it also supports the DNSSEC, then it is going to respond back. And this response will contain the information that you requested. For example, if you requested the A records, which is the IP address of the domain name, it will contain that record. Plus, it will contain three more things. One, like I said, the resource record signature, which basically contains the digital signature of the returned record, means the hash of the record or the IP address that has been resolved. So it will contain the hash of that information, and it is signed by the authoritative name server's private key. And it also contains the public key of the authoritative name server. So we call it the DNS key. And plus it also includes the designated signer, that who is the parent of this authoritative name server. Now the client will easily verify the signature because he has the public key, he has the hash. So he is going to apply the public key in order to verify the resource record that has been sent. Now the client needs to check the authenticity of the authoritative name server public key. Now the public key that was sent in the previous message, that public key needs to be verified. So how is it going to be verified? Well, when the reply was sent by the authoritative name server, he also sent the information of the designated signer, or DS. So you can see here the third information, which is DS, or designated signer. Now the client will verify or request the designated signer to verify the key, public key, that was sent by the authoritative name server. So which means that a chain of trust has to be created upon a key that the client trusts. So the client usually trusts the root name server on the, before even the top level domain. So he doesn't even trust the TLDs. He trusts only the root name server. So until this chain of trust is established, this authentication process will continue. So the client requests the designated signer record from the ANS parent. The authoritative name server parent sends to the client a designated signer record, which contains the hash of the authoritative name server public key. So when he sends the hash of the authoritative name server public key, the client, he can verify it by using the designated signer's public key, a resource record signature, which contains a signature for the DS record using the parent's private key. So he also sends him a signed message with his private key so he can verify the public key. And it also contains the public key of the parent as well, right? So let me show you in this example so it becomes more easy to understand. So this is the client, and he requested a resource record for book.example.com, right? So this record, it comes from this server, for example, and it gives him the book.example.com, and his IP address is 1.1.1. Now this resource record, it is actually signed. And who has signed it? It has been signed by his private key, right? And then you can see here, it has been signed by the private key. This message has been sent to the client. Now this server also sends his own public key along with this message. Now he can verify, because the public key is there in this message, so he can verify this signature by decrypting it with the public key. However, he does not trust the public key that is sent by this server. So he wants to verify the public key of this server. So in the designated signer information, he also sent him that, okay, my parent is example.com, right? So now the client wants to verify the public key of this from his parent. So now you can see here that this DNS key, which was for this guy, book.example.com, it has been signed by the DNS key of example.com, this key, and he sent it to him. Now he can and he also sends his own public key along with this message, right? So when he receives the public key of this server and the signed public key of this server, he can verify this information by decrypting it with his public key. But now he doesn't trust that the public key of this server. So he asks him that, okay, who was your designated signer for example.com? So this example.com tells him that my designated signer was .com. Now what he wants to do is that he wants to verify from his parent that the public key, which was sent by this server, with which I verified the public key of this server, can you verify example.com's public key because you are his parent? So now you can see here that the public key of example.com is basically, this is the hash of obviously for that. So he signs it with his private key, this whole thing. And he also sends his own public key so that he can verify. So when this information comes to the client, he will use the public key of this root.com server in order to decrypt this and verifies the public key, which was, the hash of the public key, which was for this. So in this chain of trust, to summarize this discussion, this client verifies the information signed by him, but this client wants to verify his public key. So he goes to this server to verify his public key. And then when he sends him the verification of his public key, then he wants to verify his public key from his parent. So you see here, there's a chain of trust. Now this public key of .com, this is the only public key that the client knows and he can trust. So with this chain of trust, the client is able to verify this DNS record and also able to verify their public keys of these two servers from eventually reaching the root of this trust, right? Now, it looks very effective, but it is also very complex. This is one reason that the DNSSEC deployment has become challenging. Why? Because signing the root zone is a complex matter, which means that each of the 13 root servers, they are operated in different countries or different entities. And there are political concerns with US for controlling the root level of the DNS. So this is one political challenge that is there. Secondly, the DNSSEC will add a huge amount of load on the DNS servers because the packet size will increase with this additional resource record signature, the public keys, the designated signature. So the size is bigger than 512 bytes, which is the original size of the UDP packets. The number of DNS transactions that you see that are happening in the previous slide that I explained among this chain of trust and then verifying this information, then verifying this information. So basically, the number of transactions, they have increased considerably because of the public keys and the verification and the resource record verification and chain of trust, etc. So the transactions also increase, which will take time, of course. The zone file also increases due to the addition of these increases. So the size of the zone file, they increase because of the signatures, the hashes, the public keys. And the client has to spend additional time in validating the signed data and validating the public key, potentially slowing down the resolution process. Now, remember, the DNS protocol has to be fast. And the reason why, because users nowadays, they cannot wait for the DNS to resolve the IP and then they will open the website. They want it to be done quickly. However, this process will cause delays. The server has to generate new signatures over all the resource record set changes, which places an incremental load on the server's function. So from the server side also, because he has to generate the signatures over all the resource records, then obviously this is also going to cause more delays. And especially in the content delivery networks like Akamai or Limelight, this process is really difficult to implement DNSSEC. And therefore, if you see the note from the Akamai and Limelight, they say that for our DNS mapping service, we have end users coming from all over the world to 150,000 servers. That's a pretty sizable and interesting DNS file, explains Andy Ellis, the chief security officer of Akamai. The way that DNSSEC was written was that the DNS was a static file. Most organizations have small zone files that doesn't change much, but the zone files or zone records for the Akamai, it changes very often. So it becomes difficult for them to basically implement DNSSEC. The DNS file that we have uses roughly 3.2 billion resource records to give out and sign, and we have to change them every 20 seconds. So for them, it basically is almost impossible to implement. A few years after the Kaminsky flaw, which you can read on this URL about the DNS, some of the companies, they deployed the DNSSEC. Remember, the biggest challenge in implementing DNSSEC is that it has to be implemented on the server side as well as on the client side. Only then it will be effective. Now, the US companies, they responded to this flaw by patching the DNS software, but very, very few of them, they've actually deployed the DNSSEC. And that is why we still are facing the DNS poisoning attacks even today. So the NIST survey reveals that none of the top 100 major US e-commerce companies tested by Secure64 was using digital signatures to sign their zones, nor were any of these organizations validating DNSSEC queries. The only sector in the United States that is deploying DNSSEC is the federal government, which is required by law to do so, of course. So with this, I have completed the discussion about the DHCP protocol. How does it work? What kind of attacks can be launched? We discussed DNS. How does it work? What kind of attacks can be launched? And then how we can secure it. I hope you have enjoyed the lecture. Thank you.